Welcome, everyone. Today we're diving into the copper-chlorine thermochemical cycle, a cutting-edge method for clean hydrogen production powered by nuclear heat. This is a pioneering integration with fast breeder reactor heat at IGCAR Kalpakkam, developed in collaboration with BARC and the Department of Atomic Energy. The focus here is on zero carbon emissions, a closed-loop process, and operating at relatively low temperatures. Let's explore how this breakthrough technology is shaping the future of sustainable hydrogen. So, what exactly is the copper-chlorine cycle? It's a hybrid process that cleverly combines heat-driven chemical reactions with a single electrochemical step. This means it uses mostly heat, plus a bit of electricity, to split water into hydrogen and oxygen. The cycle is fully closed loop, recycling copper and chlorine compounds, so water is the only input needed. Operating at around 500 degrees Celsius, it's much gentler than other cycles, making it perfectly suited for nuclear reactor heat, especially from fast breeder reactors. At its core, the Q-Kel cycle splits water into hydrogen and oxygen, with zero carbon emissions when powered by nuclear or renewable heat. The key advantage is that most energy comes from heat, which is less costly than electricity. It operates at temperatures achievable by current nuclear reactors, enabling continuous, round-the-clock hydrogen production. This turns nuclear reactors into dual-purpose assets, generating both electricity and clean hydrogen fuel. This is a game-changer for sustainable energy. Let's break down the 4 steps of the Q-Kel cycle. First, hydrogen is produced when copper metal reacts with hydrogen chloride gas at around 430 to 475 degrees Celsius, forming cuprous chloride and hydrogen gas. Next, hydrolysis splits water using cupric chloride and steam near 400 degrees, regenerating hydrogen chloride. Then, thermolysis decomposes copper oxychloride at about 500 degrees, releasing pure oxygen. Finally, a small electrical input at ambient temperature regenerates copper and cupric chloride, closing the loop. Now, the exciting part: India's breakthrough in integrating this cycle with nuclear heat. The facility at IGCAR Kalpakkam uses process heat from the fast breeder test reactor, providing the perfect temperature for oxygen production. This dual-purpose reactor produces both electricity and clean hydrogen fuel. Importantly, only the final electrolysis step requires electricity, while the rest is driven by nuclear heat. This indigenous technology is optimized for Indian reactor conditions, marking a significant milestone in clean energy innovation. Comparing the Q-Kel cycle with conventional green hydrogen electrolysis reveals some striking differences. Traditional electrolysis relies heavily on electricity, operates at room temperature, and is intermittent due to reliance on solar or wind. In contrast, the Q-Kel cycle uses mostly nuclear heat at around 500 degrees, demands very little electricity, and runs continuously 24/7. It also achieves higher efficiency when paired with nuclear reactors, all while maintaining zero carbon emissions. This highlights the QCL cycle's potential as a superior clean hydrogen solution. To sum up, the Q-Kel cycle uses copper and chlorine as chemical middlemen, with nuclear heat driving most water-splitting reactions and only a small electrical input needed at the end. This results in clean hydrogen with minimal electricity use and zero carbon emissions. Looking ahead, scaling up the Kalpakkam pilot, integrating with new reactors, exporting this technology, and supporting India's green hydrogen goals all point to a future where nuclear plants serve dual roles, producing electricity and clean hydrogen. This is a major step toward a sustainable hydrogen economy powered by Indian nuclear technology. Presented by Excel Laboratories for strategic discussion and informational purposes only. Thank you for watching.